Dynamic speech endpoint detection with regression targets. Dawe Liangsu, Tarun Singh, J. Mahadeokar, Shanil Puri, Jiedan Zhu, Edison Thomas, Mike Seltzer. University of Texas at Austin, Meta AI. Abstract. Interactive voice assistants have been widely used as input interfaces in various scenarios, for example, on smart homes devices, wearables, and on AR devices. Detecting the end of a speech query, that is, speech endpointing, is an important task for voice assistants to interact with users. Traditionally, speech endpointing is based on pure classification methods along with arbitrary binary targets. In this paper, we propose a novel regression-based speech endpointing model, which enables an endpointer to adjust its detection behavior based on context of user queries. Specifically, we present a pause modeling method and show its effectiveness for dynamic endpointing. Based on our experiments with vendor-collected smartphone and wearable speech queries, our strategy shows a better trade-off between endpointing latency and accuracy compared to the traditional classification-based method. We further discuss the benefits of this model and generalization of the framework in the paper. Index terms: endpointing, end of query, interactive voice assistant. 1. Introduction. With rapid development of speech technologies in recent years, interactive voice assistants have been widely adopted as a mainstream for intelligent user interface. By taking users' speech queries, these systems are able to perform a variety of tasks from basic question answering, music playing, calling and messaging, to device control. As an initial step, a voice assistant needs to determine the time point when a user finishes the query so that it knows when to close the microphone and continue downstream processing, for example, language understanding and taking action. This process is often referred to as speech endpoint detection or endpointing. In practice, the challenge for speech endpointing lies in the conflict goals of fast response and endpoint accuracy, avoiding early cuts of user speech. Specifically, a rapid close of the microphone in response to user queries brings a better user experience if endpointed correctly, but this inevitably increases the risk of early cut of user queries. The performance of an endpointing system is thus evaluated on how this conflict is resolved in practical cases. Canonically, voice activity detection has been widely used for speech endpointing. In the VAD setting, a model is developed to distinguish speech segments from non-speech segments, which usually includes silence, music, and background noises. The end of the query can then be determined if a fixed duration of silence is observed by the VAD system. However, this approach is not reliable enough, as pointed out by later work. The fact that a VAD system is typically not trained to distinguish pauses within and at the end of queries prevents the system from capturing enough acoustic cues related to end-of-query detection, such as speaking rhythm or filler sounds. Recent researches on speech endpointing mostly focus on classification methods, where a dedicated endpointer is developed to classify audio frames into end-of-query frames and other frames. The success of the long short-term memory architecture contributes to this method. Some other efforts include additional text decoding features or user-personalized I-vectors. This is to better fit the endpointer for specific acoustic environments. In an end-to-end automated speech recognition system, the endpointer may also be jointly optimized with the recognition model. Despite the promising results, all of the above works focus on binary detection of end-of-query with hard labels, for example, 0 and 1. In real scenarios, however, an endpointer shall adjust its endpointing aggressiveness based on semantic, prosodic, or other speaking patterns in the query. The traditional binary targets for classification can be less flexible in this respect. In this paper, we study a novel speech endpointing strategy based on regression method. In this setup, an endpointer is optimized to fit soft-coded targets during training, and the training targets are set by considering expected pause given semantic context of the queries. By testing on both 14.4 million smartphone speech queries and 467,000 wearables user queries, we show that our proposed method effectively reduces the response delay of endpointing while maintaining a comparable accuracy performance as the conventional classification-based method. 2. Regression-based endpoint modeling. 2.1. Principle. In a traditional classification setup, a speech endpointing model is trained against targets of hard-coded values, 0 and 1. At prediction stage, a decision threshold is picked and compared against model output endpointing confidence. In a regression setting, the prediction stage remains the same, but the training targets are changed to be continuous float values from 0 to 1, representing the confidence of a frame being part of end of query. Specifically, we apply a transition curve to the area between user speech end and the expected endpoint position, that is, position where we are confident to endpoint. Figure 1. Sample targets for endpointer training based on hard-coded binary values, target in black, and soft-coded float values, target in red. EP endpoint. The motivation of our regression-based modeling includes 1. The model should have an increased confidence in endpointing as more silence is observed. 2. The aggressiveness of the endpointing behavior shall be adjustable, which corresponds to the slope of the transition region. As an extreme case, a regression model with 0 transition region would have the same targets as a classification model. The top plot of Figure 1 is an example where the training targets of a regression model and classification model are the same. At the bottom, the regression target enforces the model to be less aggressive, with a smoother slope in the transition region. Figure 2. The overall pipeline of our proposed method. Figure 2 presents the overall pipeline of endpointing with regression. To enable a dynamic output behavior of the endpointer, the transition slope of the training targets can be quantified based on unique patterns, for example, expected pause of individual input queries. In this paper, we propose a method to compute and leverage the pause statistics of queries for this purpose. Section 2.2. During inference, the regression model shares the same setup as the classification model, i.e., taking speech features as inputs and applying a decision threshold to the model outputs for endpoint decision. 2.2. Loss function. In our study, we use the mean square error, MSE, as loss function for endpointer training. The loss function is defined as below. L equals the sum from I equals 1 to n of y hat I minus yi squared divided by n, where I is the ith frame of an utterance in the dataset, n is the total number of frames in the dataset, y hat I and yi are the output of the endpointer and training target, respectively. In our experiments, we found that regression with the binary targets yields the same performance as the traditional classification setup. Furthermore, the MSE loss tends to be more stable for model convergence than the L1 loss. 3. Speaker pause modeling. To enable dynamic adjustments of endpointing behavior, we explore the expected pause following a speech segment. Our intuition is that ideal endpointing aggressiveness should be controlled by the expected pause following a query, and the expected pause is related to semantics. For example, the chance of a speaker continuing speaking following an utterance, "What's the weather?" is bigger than that following the utterance, "What's the weather in Seattle next week?" By calculating the expected pause following a speech segment, we can adjust the slope of the transition region to be smoother for the first utterance, so that the endpointer can learn to wait a bit longer for the first utterance than the second. We hope to estimate the expected duration of each training query and use it to adjust the targets for these queries. We model the pause for a given text context as a Gaussian variable. T sub f follows normal mu sigma squared. Here, Tf is the pause duration for a text query, C is the text context of the query, and mu and sigma are parameters for the Gaussian variable. The parameters of this model can be estimated by 4. Experimental setup. 4.1. Data. We use 2 datasets to evaluate our method. Both are collected by third-party data vendors. The first one is collected using smartphones, whereas the second one is collected using wearable devices, smart glasses. We refer to the 2 datasets as smartphone data and wearables data in this paper, respectively. The smartphone dataset contains clean user speech that are spoken in fluent manner with little background noise. In total, 14.4 million queries were collected, categorized into 55 domain contexts based on the text transcription. The most common contexts are music, 1.4 million, weather, 1.3 million, and device handling, 1.2 million. The average word count per query is 6. The wearables dataset is collected when users interact with a voice assistant on smart glasses with real-life noises in the background. A considerable amount of speech pauses and disfluency are identified in this data. It contains 447,000 queries with an average word count of 11 per query. Both datasets contain speech and ground truth transcriptions. Ground truth speech endpoints are calculated by aligning speech to transcription and measure the last word end time. From the alignments, we can also collect pause duration, if any, following each word in the queries. For both datasets, we randomly split the queries with a ratio of 95:5 for model development and testing. A development set was further split out in random during training for learning rate adjustment. The training set and testing set share the same set of speakers. 4.2. Model configuration. Our endpointer is an LSTM neural network inspired by prior work. Specifically, the model consists of 3 unidirectional LSTM layers with a hidden unit size of 128 per layer. For the baseline classification model, the output is a fully connected layer of 2 neurons, transformed by log softmax activation. For the regression model, the output contains only a single neuron with sigmoid activation. During training, the baseline model leveraged the regular cross-entropy loss, while the regression model uses MSE loss. The learning rate was 2 times 10 to the power of -4 times 2 times 10 to the power of -3 for each model, and reduced by a factor of 0.5 if no improvement was observed on the validation set. The Atom optimizer was used with a beta of 0.9, 0.999. The mini batch size was 128. Besides, a sliding window of 10 milliseconds was applied to the outputs of the baseline model at prediction stage for score smoothing. Both models were trained for 15 epochs when learning rate drops to a small enough value. All development was done using PyTorch Toolkit. We extracted 35 binary features as inputs to the network. We extracted these features based on a 25 millisecond window and a stride of 10 milliseconds. The sampling rate of the audio was 16 kilohertz. 5. Results. 5.1. Overall results. In total, we obtained 166,018 unique prefixes, respectively, for the smartphone and the wearable training sets. Following the prior work, we applied the early cut rate as the model accuracy metric, which reports the proportion of early cut queries out of the entire test population. We do not use DWER as a good endpointing metric because we think it is not linearly correlated to endpointing accuracy, and thus not linearly correlated to user experience on endpointing. Specifically, an early cut in the beginning of an utterance and at the end of an utterance are both early cuts and both cause users to repeat their queries, but their DWER differs greatly. For the latency measure, we use the 50th, 75th, 90th, and 99th percentile statistics of latency values out of the predicted results, noted as P50, P75, P90, and P99 respectively. For both metrics, a smaller value is more desirable. Tables 1 and 2 summarize the overall model performance of our study based on sample decision thresholds from around 0.5. Given the closest early cut rate for each pair of comparisons, we can see that the prediction latency measured by P50, P75, and P90 tends to be improved by the regression model on both. 5.2. Discussions. To further study the potential of generalization for regression-based endpointing, we visualized the model outputs based on a simpler setting. In this setting, the training target slope of the endpointer was adjusted by handcrafted criteria based on the max pause duration within a query, 0 to 10 milliseconds slope duration, greater than 90 milliseconds to 100 milliseconds slope duration. Figure 3 shows the predictions of the regression model for 2 sample queries. It can be seen that the regression model can achieve the same output behavior as classification-based endpointing for a query with little within-sentence pauses. Top plot. However, the output of the regression model is smoother for a query with significant within-sentence pauses. Bottom plot. The plots help to demonstrate that regression-based endpointing can be applied to different target adjustment strategies. In addition, we noticed that regression-based endpointing can help to maintain the model stability for endpointers of lower complexity. In an extra study, we have the hidden units of the LSTM layers for our neural endpointer. By testing with the noisy data, the early cut rate of the regression model increased to 18.77% at a threshold of 0.5. The P50, P75, P90, and P99 values also increased to 380 milliseconds, 550 milliseconds, 970 milliseconds, and 2,370 milliseconds, respectively. However, at the closest early cut rate, 27.95%, threshold equals 0.81. The P50, P75, P90, and P99 results of the classification model significantly increased to 1,770 milliseconds, 2,260 milliseconds, 2,480 milliseconds, and 2,690 milliseconds, respectively. A possible explanation is that the abstraction of the unique prefixes from the original queries helps to generalize the endpointer on the patterns of the queries. This benefit is meaningful for endpointing on the edge, especially for devices with limited computational capabilities. 6. Conclusion and future work. In this paper, we proposed a novel regression-based speech endpointing model, which points to a new direction for solving the early cut issues in endpointing without sacrificing latency. We then describe how we utilize this model for dynamic endpointing by adjusting training targets based on expected pause of speech queries. Based on experiments with speech data collected by smartphones and wearables, the proposed regression model shows a better performance on latency accuracy trade-off, with an improved P50, P75, and P90, specifically, while maintaining a comparable early cut performance to the traditional methods. This regression-based endpointing approach is quite flexible and can be used to incorporate speaking behavior modeling in the future. A better pause model can be explored by grouping utterance into semantics rather than pure prefixes as well. This concludes the reading of Dynamic Speech Endpoint Detection with Regression Targets on Research to You. If you would like more papers added, please leave a comment. If you would like to be notified when more papers are available, be sure to subscribe, like, and ring the bell.